We already started the testing and verification model of the model number 5, and we already undergone some of the timing and synchronization circuitry what we are going to use for the implementation of a sequential circuits. And we studied about in the previous classes one of the fundamental sequential circuit implementation, that is a JK flip-flops we have studied, and what are the design methodologies we are going to study it, and what you mean by race around conditions we studied, how we are going to overcome this race around condition by the use of master and slave JK flip-flops we have studied. And the implementation of this master and slave JK flip-flops has been highlighted in this diagram. You can see we can able to implement the master and slave JK flip-flop by using a universal gates, that is nothing but NAND gate and a NOR gate. And after studying all these principles, the next and fundamental thing is to go for the testing and verification. So we have already covered all the aspects of the design which is related to VLSI subsystems. So we initially in the module number 1, 2, 3, and we studied about how we can able to design the system by using elementary elements, and then in the module number 4 we studied about what are the architecture principles we need to consider before we go for the selection of any architecture. And once you do that, what are the different principles which will enable us to go for the optimization of the architecture what we have selected for the design of a VLSI subsystem. All those details we studied about. In this model number 5, what we are going to do is we mainly concentrating on the synchronization mechanism of the clock signals, that is a timing constraints we studied in the chapter 1, that is part 1 of the model number 5. And in the model number 5 in the chapter 2, we are going to go for the how we can able to do the testing mechanisms and what are the verifications tools we are going to use in the VLSI subsystem we are going to study. So in order to, before we go for how exactly we go for the testing of the each component of the VLSI subsystem and verification. So this is the functional way of that is the abstract level of how we go for the flow diagram of the verification process. So the first process is, as I said, we are going to go for the behavioral specifications. So this behavioral specification is the second step in the design flow of the VLSI subsystem design. So in the first step, as I said, we are going to take the customer's specifications, that is the specifications we are going to derive based upon the customer's needs, and along with the specifications we are going to go for the, or we are going to mainly concentrate on what are the constraints that the customer is imposing and what are the design principles we need to select for that. So that we will be doing it in the step number 1. So after selecting the design architecture, the next step is to divide the given complex circuit into fundamental or individual independent smaller groups, and these smaller groups we are going to do this implementation or the simulation we are going to do it. So the simulation of each subsystem of the entire architecture we call it as a behavioral specifications. So we need to arrive at the behavioral specifications, means what is the input and output relationship between them, we need to arrive at for the each subsystem. And also when you divide the given complex process or the complex application into several subdivisions, it is necessary for us to make sure that a minimum communication is required from one subsystem to the another subsystem during the implementation wise, so that it will be easy for us to test and debug each individual subsystem without any coordination between the one system with the another subsystem. So that will ease the design process, and also it will ease us to debug the process as efficient as possible. So once we arrived at the subsystem specifications, the next one is to implement how we are going to do the implementation. So we use the simulation software. Generally we are going to use VSDL or Verilog or system Verilog we are going to use in order to do the simulation of the particular subsystem of the VLSI design values we are going to do it. And then after arriving at the behavioral specifications, the next one is what we do is we go for the synthesis. So means what, we go for error checking methodology. So if there is no error checking methodology or we have successfully run the syntax errors, means then we go for the RTL specifications. So in the RTL specifications, what we are going to do is how many number of the logical elements we have used for the implementation of the behavioral specifications. So all those details we are going to see it, and along with that we are going to see for the timing constraints. So whatever the timing constraints we discussed in the earlier classes, so we are going to see the timing constraint specifications for the RTL schematics. So once the RTL schematic has been successfully implemented with the timing constraints, the next one we go for the structural specification. So means what? The fabrication process which is related to the implementation of the RTL specifications, we are going to do it. Okay, so that part we call it as a structural specification. So in the structural specifications, what we do is for each circuit we go for the stick diagram implementation, and once we analyze the stick diagram implementation, that stick diagram we are going to convert it into a mask layout, and then from the mask layout we go for the physical implementation. So when we go for the structural specifications, we consider about the layout and the schematic. So what exactly the layout we have discussed. What is the layout at the initial stages of the design we have considered, and how exactly the schematic has been arriving through the use of RTL specifications we are going to see it, and also the power optimization techniques or the power budget of the each subsystem implementation we are going to see it. Okay, so all those details we are going to run, or the modeling of these parameters will be done in a structural specification. So after doing the structural specifications, the next one is the physical specification. In this physical specifications, what we go for the implementation. So means we go for the fabrication process. So once we do the fabrication process, it is necessary for us to do the testing component. Okay, so means what? The manufacturing, the product is ready and it has to be delivered to the customers. So before it has to be delivered to the customer, what we do is we go for a rigorous testing, and the desired output whether we are going to get it, and the environmental conditions whether it is feasible for that application or for that product to work in efficient manner. So all those details we are going to do it in a physical specification. So in this specific physical specifications, we have different types of tools are available for the debug and for the verification and testing of each component, and for the different test cases. So if we are getting the desirable output for all the test cases, means then finally the product will be handed over to the customers. So these are the testing and verification process what we are going to use in the VLSI system design implementation. Okay, so next in the verification process, we go for a different types of testing mechanisms. The first we call it as a test benches and harnesses. We go for the, in the test benches, what we do is, yes, we have created a behavioral simulation for the particular subsystem. That is, let's say we have implemented a full adder circuit. So for this full adder circuit, what I need to do is, so let's say you have a full adder circuit, means we have a 3 inputs and 2 outputs you have, that is A, B and C in you have, and 2 outputs you have, that is sum and carry. And what I should do is, for all the input cases whether I am going to get the desired values or not, I need to check it. Okay, so therefore what I am going to do is, in the behavioral simulation I go for the creation of test benches. So in this test benches, what I will do, I will create all the combinations of the input sections, starting with the 3-bit means 0 0 0, that is the first stage, and the final input stage what we can get is 1 1 1. So for all these cases I need to make sure that whether I am going to get a correct realization of the sum expression and carry expression, I need to see it. So we are going to create a test benches. So through the use of these test benches, we can able to see the desired output whether we are going to get for the simulations we are not, we are going to check it. And the next one we call it as a harness. So what do you mean by harness is, so you can see it is a collection of steps, drivers and other supporting tools which is required to automate the test execution. So we have some built-in test we have, that is a simulation tools we have. So with the use of these tools, it is possible for us to do the automation for the test execution. So means what, if I run an any circuit means, so for that circuit, so I will be feeding the different combinations of the input signal. So directly it should execute the program and it should give me the desired output, or it should give me the output. So based upon the output what I am going to get, so based upon that I can say that how best I am getting the output. So if your error is free means, then we call it as a less harness we can able to expect. If there is any mismatch in the desired relationship between the input and output means, then we get a higher amount of harnesses we will be getting. Okay, so here in this harnesses, We will be using some test libraries, and these test libraries will generate reports based upon the output what we are going to get from this text tools. Okay, so this test harness will contains all the informations which is necessary for us to do the compilation and to run for all the test cases, and all these test cases will be deployed onto the target deployment port. So what do you mean by this target deployment port is, so this is the port where we want to run our simulated code. So I am going to deploy all these under this target deployment port, and I will be making sure that my harness, that is a test harness, will be as low as possible. And along with this test benches and harnesses, we go for different types of means verification process, that is the logical verifications we go for, and these processes or principles we call it as a regression testing, version control, and bug tracking. So let us see what you mean by regression testing. A regression testing, it is nothing but it is a gate level functional verification. It is imperative, means it is very necessary for us to do the gate level functional verifications in order to provide solutions if there is any undesirable output you are getting based upon the input and output relationship. Okay, so we go for the regression testing. So in this regression testing means the test output what we got from the harness tools. So if we are getting an undesirable output means, then we go for this regression testing. In this regression testing, we go for the gate level functional verification. So if we already know that there are some already debugs there are already bugs are appearing in our simulation tools, and how these simulation tools are expecting or producing the bugs, we need to understand. So in order to understand the errors which has been generated during the verification process, we go for this regression, that is a testing. Okay, so this is, we call it as a gate level functional verifications, we are going to call it. The second one is the version control. The second one is the version control, and this one version control, it is also sometimes we call it as a source control. Okay, so what do you mean by source control is, it is a practice of tracking and managing changes to software codes. So we have written already some codes out there, and we want to do some changes in the code, means then it has to be updated and it has to be noted down. So during which other time we have changed the code, and who is that has the changed the code, and why he has changed the code. So all those details we need to update it, and those updations, it is necessary for us to do the recording, or it has to be done, it has to be structurized, so that in the future if you want to do any changes in the software what we have written, or the code what we have written onto the software, so it will enable us to do the changes for the source code over the time. Okay, so that we are going to call it as a version control. And the next one we call it as a bug tracking. So what do you mean by bug tracking? You can see here, it is a process of logging and monitoring bugs or errors during software testing. So when we are doing the software testing, whatever the code we have written for the behavioral simulation, either it may be VHDL Verilog or it may be system Verilog, we need to monitor the errors, or we need to monitor the bugs which we are going to do during the software testing. Okay, so with the use of this bug tracking, it will enable us to where exactly the issues has been generated, and with the use of these issues we can able to identify, or we can able to rectify the defects which is there in our code. Okay, and sometimes the system may generate some several thousands of defects it may generate. So it might be the test cases also, or it might be the input what we are feeding for our system code. So if the input what we are feeding for the system code, it is not compatible, means then thousands of errors will be generated. Or if the input what we are feeding for the system code, if it is correct, then we will be getting a minimum number of bugs we will be getting, depending upon the port mapping, how it is going to take in the RTL schematic. It is necessary for us to understand. So that is why, so this bug tracking enables us to do the debug tracking of if there is any issues is there in the source code during the implementation of the applications. Okay, so this is what we are going to use in the bug tracking. Okay, So these are the previous, now whatever we have studied this logic verification, that is test benches, harness, regression testing, version control and bug control, that all these we call it as a behavioral simulation or a logic verification. So as the name indicates, it's a logic verification, means the verification part we are going to do for the software code. So we call it as a logical verification. Now we have written the program and we have simulated the program and we got the RTL schematic and everything is there, and finally I go for the manufacturing. So before I go for the manufacturing, I need to make sure that the hardware description language, that is whatever the programming language we have written, so for the physical devices or the circuits what we have generated, so for that generated circuit, is there any fault has been occurred because of the mismatch in the timing constraints, it is necessary for us to know. So therefore we go for the next, call it as a manufacturing test principles. So in the manufacturing test principles means we have already implemented the circuit by the use of fabrication process. So once I done the manufacturing, whether I am going to get the desired output what I was getting before the manufacturing process, I need to do it. So for that we need to use a different test cases or the test principles we need to do it. So all those test principles now we are going to look into in those issues in the subsequent chapters or the subsequent sessions. Okay, so you can see here one simple example of what you mean by test principle is, so we have implemented some combinational circuit we have implemented, and for all these combinational circuit it is necessary for us to check the input and output relationship, whether I am getting the desired output or not. I need to check for this combination circuit. So if I consider the previous example what I have done, so we have considered the full adder. For the full adder, how many input sections should be having is 2 power 3 is 8 input section it is necessary. See, it is not that if I want to do the testing operation for my full adder whatever I have designed is, I need to check for all the test cases. No, that is not the cases. What we as a optimum designer or the optimum software debugger, what they will do is they will check some specific input signals or the specific input combinations. So for those specific input combinations, whether I am going to get the desired output or not, I need to check it. So means as a design engineer, we will not go for the entire different combinations of the input sections to check whether I am getting the proper output or not. I will be checking some important specifications or the important the input signal combinations. So for those input signal combinations, whether I am going to get the proper output or not, I need to check it. So those inputting values we are going to give it from one more additional combinations, and those additional combinations we are going to call it as a text circuit, or we call it as a text principle. So you can see here we have a combination circuit. So for this combination circuit I have added one more called as a resistors. So through the use of this resistors I can able to feed the additional input sections what I want to test is. So based upon the input signal what I am going to give for these resistor combinations, so I can able to do the testing operation for the combinational circuits. And the next thing is, so whether once I do the testing of my manufactured product, whether I am going to generate a faults or not, we will be checking. So obviously we will be getting the faults. So how you manage those faults? So how you categorize the faults? On what basis you say that it is a fault? So all those things we need to understand. So in order to categorize or in order to understand the different faults which has been exerted or it will be generating during the VLSI manufacturing subsystem, we need to necessary to understand the fault model. So we call it as a struck at 0 model, we call it as a struck at 1 model. So generally these are the faults where we are going to get. So what do you mean by struck at 0? Struck at 1 is, so at all the cases the output may not be switches from 0 to 1. So this we call it as a struck at 0. So if the output is not changing from 1 to 0, we call it as a struck at 1. Okay, so for all the cases we need to do some additional combination circuits or a sequential circuit in order to analyze whether it is a struck at 1 or a struck at 0 fault we need to identify. So this is one of the simple combinations what we have used, that is a struck at models for the CMOS implementation. for the circuit what we have created for this combination circuit. So for this combination circuit I will be adding this fault model, and based upon the output what I am going to get for this fault model, I can able to save whether it is a stuck at one fault model or stuck at fault zero model. So depending upon the output of this, I can able to go for the next process of verification or a testing mechanisms.